999. Oh, 1,000. Oh, that was tough. And in the time of Corona, we need to keep in shape and do what we can to keep from going crazy. And whenever I'm in my home gym basement or at the gym anywhere, I start thinking about power. And when I'm thinking about power, it naturally makes me think about power analyses and effect sizes. So an effect size is something that would be helpful for determining how big a test statistic is. So you might not realize it, but you've probably already heard of some effect sizes. Something like an adjusted R squared, for instance, is an effect size. But let's think about those t-tests for a minute. With those t-tests, we have two groups, and we're going to compare the means of those two groups. So what we could get into is a situation when the absolute difference between those groups kind of betrays the true size of that difference. So let's say that we have two different groups, right? We're going to compare groups one and group two, and then maybe also group three and group four to each other. And we're going to kind of see what this may look like. So let's check this out. Let's go to this handy little paint app here. So here's what we're going to do. I'm going to draw some lines. So here's a line that would be a mean. Trust me, it's straight. It may not look like it. Maybe it's just your resolution. And here's another one, just as straight as the first one. So what we could get into is a situation where, let's say those groups one and two, let's say it kind of looks like a distribution like this, right? Okay, there's some distribution there. And let's say that this group two kind of has a distribution like this. Let's go ahead and level out the tail over here a little bit more, right? Okay, so, but let's also take another look at some other groups, right? This group three, for instance, may have a distribution that looks like this. And group four may have a distribution that looks like this. All right, again, those are lined up, I promise. Again, maybe just a resolution problem on your end. Do some more reps and that ought to clear it up. But what we see here is that those groups on the top, these right here, there's a difference in the means, but we have a lot of overlap in these distributions. Now, there's not a ton, but there's certainly some. Let's look at these groups three and four, though. We can see that the difference in the means of these distributions is the same as in groups one and two, but there's no overlap between groups three and four in terms of their distributions. So if we had to look at something like this and say, well, what's the bigger effect? It's probably between those groups three and four, these groups on the bottom, right? So although those absolute values are the same, right? The absolute values of the differences are the same. There's a bigger effect here between groups three and four than there is between one and two. So this is part of what effect sizes can tell us, is that they give us kind of a standardized way of talking about these effect sizes. So something like the Cohen's d for t-tests becomes a really helpful tool for knowing just how big that effect is. Yeah, we can look at that t statistic, and that t statistic, if it's above 1.96 or below negative 1.96, we know that it's big. Now, how big is it? Is it fake natty, or is it actually big? That's where the effect sizes come into play. So Cohen has some rules of thumb that are out there for you to look at in terms of what's a big or a small or a medium effect size. But it's kind of one of those things that, again, like all rules of thumb, they can kind of break down a little bit. But that's roughly what an effect size gets us. Now, effect sizes also have this other little bit of information that they can be helpful with, and that gets into power. So when we're talking about statistical power, we're talking about the probability that we reject the null hypothesis when the alternative hypothesis is indeed true. So essentially what we're trying to do is we're trying to minimize our risk of type 2 error when we're dealing with power. So power and effect size are linked through sample size. So if we have a large sample, with a large effect size, that's going to probably tend to produce a large power value. And power ranges from 0 to 1. The higher it is, the better. So that's on observed power, right? So that's what we're talking about there, from 0 to 1. But if we're doing this in an a priori, so before we collect any data, right, that's going to tell us how large of a sample we actually need. So we tend to set power to 0.8. That 0.8 is just kind of a standard value. What we would see is that if we take our effect size, and if we essentially the larger our effect size, the fewer people we need, right? So if we expect that there's going to be huge differences, we need fewer people in any group to find those huge differences. On the flip side, though, if we have a small effect, and in that small effect, right, it doesn't mean that it isn't a real effect. It's just a small effect. But if it is a small effect, what we're going to find is that we need a lot more people to detect that real effect. So it gets it's kind of a fun thing to mess around with and to learn a little bit more about. You've probably encountered rules of thumb at some point in your life, and those rules of thumb can be guides, but that's all they are. A power analysis is the only way to know how many people you actually need to have to do what you want to do. Because if you would anticipate needing very few people, then you'd better have a huge sample, or excuse me, a huge effect size. The only time you can get away with a small sample is if you are going to have a large effect. And the reality is, we're probably not always going to have a large effect no matter what we're dealing with. So don't be don't play the wrong side of this game. Always anticipate a smaller effect size. It doesn't hurt to have more sample than what you need. No harm will befall you for that. The more people that you can collect, or records or whatever it would be, the better it will be, the more powerful your analyses will be. So this is kind of a weird concept to play around with, but it's one that certainly will go a long way to helping you kind of demystify how many people that you would need to actually have meaningful results for the work that you want to do. So until no, you're not. No, you can't. You cannot squirrel in this. No, you can't curl in the squat rack over here. No, Bradley. There's always a Bradley or a Chad at the gym. Even your home gym. It's amazing. No, you'll have to curl over there. I got to get this guy out of here. This is outrageous. Until next time, I'll see you later.